applying machine learning to some real engineering problems, usually with customer companies. Oh, anticipation, I'll be able to see it down here. Right, is the slide clicker working? No. No. Oh. Whilst they're doing that, so we'll see on the next slide that one really big challenge of engineering applications of machine learning, in our case in designing new materials, is that you cannot just find the strongest material in the world or the lightest material in the world, because real life applications need the material to simultaneously satisfy a whole slew of different properties. It's got to be simultaneously cheap, lightweight, strong, and so on. But the training data that we have access to, getting it from a variety of academic papers, spec sheets online, don't always measure every property about every material. And therefore, the information that we have access to is going to be inherently sparse. There's going to be a lot of missing values. This is going to make it really difficult to apply standard machine learning techniques, because after all, they're just a mathematical formula, and a mathematical formula needs all the inputs present to give an output. And so today I'm going to show how we have actively pursued two different approaches in order to overcome this huge hindrance of sparse data. In the first approach, we're going to put the human right in the loop and be able to exploit relationships between different material properties. For example, a good electrical conductor is also often a good thermal conductor. And in the second approach, oh, will it work down here? Oh, there we go. Perfect to you. Oh, switch. Yes, stop. And so there we've got the property relationships. And in the second approach, we're going to see how we can use design of experiments to tell us which additional measurements to perform to get maximum value from those expensive and time-consuming experiments. Switch. Oh, this is brilliant. I don't need this. Right, so just a quick sort of overview of what our machine learning is going to look like. I think we've seen this before. We start out on the left with the composition of the material, but also the processing parameters. At what temperature do you hold it, for how long? Those are going to be numbers we'll put into our machine learning black box on the here, and over on the right, it will predict for us those material properties that we are interested in. Here, the number of defects formed, the fatigue life of the material, and also the strength. Now, we're going to need to train our machine learning. Next slide, please. And in order to do that, we need to send it here to university. It goes to the library, it gets access to historical materials information, train up that machine learning tool. And on the next slide, we'll see that we can then give it a fresh composition and processing parameters that it has never seen before. And within a millisecond or so, it will make an estimate for those material properties. This is a lot cheaper and quicker to do than an experiment. And then to do the inverse problem, we can get the tool to cycle through millions of possible material compositions until it hits upon the one that has the appropriate material properties.
Sorry, we just heard from Zoom that the slides are not showing correctly, so we're just trying to reshare them.
Goodness me.
There we go. I think, is this looking good? Excellent, thank you.
That's perfect. Next slide, please. Yeah, so our example use case for doing this was working with Rolls-Royce to design a new alloy for their gas turbine, their jet engines. Got a schematic of one here. Well, air goes in the left, fuel is burnt at the center, it gives off a lot of energy. The hot gases rush out the back to push the plane forward. But in particular, we're interested on the next slide of designing in one of the critical components, which is right here at the heart of the engine where the fuel is being injected and burned. And we can see in this cutaway that it's a very intricately shaped component to get the perfect mixture between fuel and air to extract as much energy out of that fuel as possible. Now, that component was made by a combination of casting and fabrication, but Rolls-Royce want to turn to a new manufacturing process, additive manufacturing or 3D printing, in order that they would be able to make an even more intricately shaped component to get the airflow absolutely optimized. However, in order to do this, they need a new material. They're going to need a new material because 3D printing is a difficult process with its own challenges, and they need an optimal material for that. And furthermore, we need to remember that to make this engine more efficient, you can also burn the fuel hotter, in fact, hotter than the melting point of the materials within it. And so we're going to need some really high-tech materials that can be strong and resistant at those extremely high temperatures. So on the next slide, please, we'll be able to see the 3D printing process taking place. In this instance, they were interested in direct laser deposition, where if we look up at the slide, we can see coming out of the nozzle here, these 3 jets of metallic powder being blown onto the component. And then down here through the middle of the nozzle is a laser beam outside of the visible spectrum, which is melting that powder locally onto the material. Now, one of the crucial words there is locally, that we are heating the material up locally to melt it, and then it cools locally as well. And so you get a lot of thermal expansion and contraction during this 3D printing process. And that means that the material expands, contracts, you get cracks, defects, and pores formed in the material, which reduces the quality of the component. And so we're going to need to discover a new material that will be resistant to the formation of those cracks and have many other good properties for its ultimate use inside of the combustor. And so on the next slide, please, we can see how we're just starting to set up a machine learning tool to do this. We, on the left, taken the composition, and we're going to be estimating the number of defects formed in 3D printing. However, we're going to hit an immediate problem, and that is that over on the left, there's around 30 parameters or 30 variables we will need to specify. There are the elemental concentrations of about 20 different metallic elements one might consider putting into this alloy, and another 10 variables that describe the 3D printing process, which could, for example, be how much power to put through the laser and how quickly to scan the laser across the object. But on the other hand, because when we did this project, additive manufacturing was a new process for this family of alloys, we had just 10 experimental data points available for how many defects form in 3D printing. And whichever way you look at it, 10 data points is not very much. We know from our school level maths that to specify 30 variables, we're going to need at least 30 pieces of information. The simplest machine learning model we could possibly fit to this system is going to be a hyperplane, and to fit a 30-dimensional hyperplane, we need 30 pieces of data for the gradient in each direction, plus one more piece of data to get the offset of the plane. And so frankly, it looks like we're stuck. We just got an impossibly small amount of data. But this is where we can sort of use our active learning approach. We can put the human in the loop and think of a really cunning plan of a way of skirting around this issue. And in that instance, it's to be inspired on the next slide, please, by some physical understanding. And that is to notice that in direct laser deposition on the left, you melt the material locally using a laser beam. Over on the right, we've got a different manufacturing process or welding where you melt the material locally, but using electricity. And so both processes sound similar. They've both got that same local heating, thermal expansion and contraction. But welding is a much older process, and so we have much more data about it. And so perhaps what we can do is look for a material that would be good at welding, and then we would hope that it would also be good for 3D printing. Now, to see that in effect on the next slide, we've got here our refreshed machine learning model, in which we're first going to learn how we go from those input variables to predict how many defects are formed on welding. Now, we've got about 1,000 data points for how weldable these alloys are, which is about enough in order to build a reasonable machine learning model. Then on the next slide, we've got a second step in which we take the weldability prediction, pass it through a second and separate machine learning model to predict the number of defects formed on 3D printing. Now, we don't have much data for this second step, but it's basically just fitting a straight line in one-dimensional space. And to fit a straight line, you need 2 data points. To know that it was a straight line, you need 3 data points that were collinear. And so suddenly the 10 data points that we have available seems almost an embarrassment of riches. And so this is the sort of almost magical process we're going to follow. We're going to do 2 stacked interpolation models to give one what appeared to be mathematically impossible extrapolation around the outside. And so that's the kind of approach that we're going to be following to exploit relationships between different material properties to overcome extremely sparse data. And the skill in developing such a machine learning model is going to be to think very hard about these analogous physical processes and to put in those that are relevant, but to not go overkill and put in too many, because then the machine learning model will effectively overfit or find some process that looks like it's correlated, but isn't in real life. So with that set up on the next slide, we can then go back to the engineers and we can talk to them and ask what do they actually want from that alloy. And I've got listed here all of the properties they require. So up the top, we've got the cost, that it's always essential that the alloy will be cheap enough to be commercially viable. And next one down is density, that the alloy needs to be light enough that the plane will actually be able to take off. And then going down, interesting. Oh, you can just about see here defects there. That's the number of defects formed on 3D printing that we need less than 0.15% of the material to be cracks, defects, pores in order that it would pass quality control. And down the bottom, we got loads of properties about the strength of the material. So of course, there's also some other these proxy quantities like weldability that the engineers that are making the engine don't care about, but our machine learning is going to need to know to help predict these. So I mentioned weldability, which is off the bottom of the slide here. It doesn't have a target on, but we must be able to predict it. And then there's also going to be several others. We've got various types of thermodynamic calculation to help understand the phase behavior of the material and so on. And so some poor PhD student had to go off and collect data for all of these different properties from various sources, put it all into our machine learning tool. It could go off and automatically identify these property relationships, use them where they were helpful, train a machine learning model. And then we had a tool that could predict all of these properties in about a millisecond or so. And then we could just get it to scan through millions of different materials until it would find the composition and processing parameters that fulfills or is most likely to fulfill this set of targets here. So if we go to the next slide, please, we'll be able to see this is the actual alloy that we designed. We've got here the composition. It's mostly a nickel-based alloy with some other additives in. And we can see, firstly, that it's very complex. It's got 10 different elements in it, which is a lot compared to contemporary high-tech alloys, which have maybe 5 or 6 different elements. So those contemporary alloys are restricted just by the fact the amount of experimental time it takes to go through all of those composition permutations. Whereas here, because we're doing machine learning, we can explore composition space very rapidly and are able to come up with, just explore new virgin territory, and that immediately gives us an opportunity to find something better. We can also note in passing that for those of alloy enthusiasts, that a lot of elements make this a fundamentally high entropy alloy, which just fundamentally gives it excellent properties at high temperature. Now, we also specify here the processing parameters down in the bottom right. There's several more, I've just shown a couple. There's the exposure parameter, which is a bit like how much oomph do you put through the laser beam, and also a post-printing heat treatment that one applies. So with that, actually, my work is done. We can pass the composition across to colleagues, the Professor Howard Stone's group at the Rolls-Royce University Technology Centre in Cambridge, who could go off and kindly print this alloy and measure it. So on the next slide, we'll actually see the alloy printed. This is what it looks like under a microscope. You can see that it's got some gray and some black. So it's a two-phase alloy. The black are some precipitates that are formed in it. We can measure what those precipitates are. We can measure their size to make sure they are what we expected and are required in order to make this what is called in the field not just an alloy, but actually it's called a super alloy due to its promise of excellent properties at high temperature. But what we can also see by looking at this microstructure is there are no obvious huge gaping cracks in it, that it looks like it has printed reasonably well within the 3D printing process, but perhaps we should go and measure this number of defects more formally. And firstly, just to remind you on the next slide of the targets that we were looking for, highlighted here in orange, that we wanted less than 0.15% of the material to be defects. So on the next slide, we'll be able to see us measure it. We've got here a graph on the y-axis is the number of defects that were formed. So we want to have few defects. We want to be in that lower gray shaded region of the graph. And on the x-axis, we show this exposure parameter. That's the amount of oomph you put through the laser beam. So we recommended an exposure parameter of 0.8, but because frankly, it was so difficult to do that machine learning, we paid a lot of money to have the sample, the material printed at several different exposure parameters so that we could then understand how the property, the number of defects varies in that space. So we can see those experimental results here with those purple points, and we can see that at our recommended exposure parameter, that indeed the alloy's worked, it's got few defects. This would be a suitable quality for 3D printing. But if we had or the machine learning had misunderstood the effect of the exposure parameter, we might have recommended one that was lower over to the left-hand side of this graph, where we can see that the alloy would not have worked. And so this is great. It looks like we were able to design here an alloy that was good for 3D printing. And we also had to go off and measure lots of other properties about the strength and the oxidation resistance and density and so on, which unfortunately I don't have time to show you today, but if you're interested, you can go read about them in this paper. And so we can see here in this first part of the talk, how by putting the human into the process and thinking out of the box, we're able to use a very cunning approach to circumvent the sparse data. But now going on to the next slide, in the second part of the talk, I want to show you a completely different methodology of overcoming the sparse data, which is the more brute force, let's collect more data. So this is a project that we did under the auspices of Project Medal, UK government-funded project, where we work with a variety of different research organisations and universities. In the bottom left, we worked with AMRC, the Advanced Manufacturing Research Centre at Sheffield. We worked with Boeing, who are providing, of course, the use case. We were working with Constellium, a company that makes metals, metallic powders. And we were working with General Electric Additive. who provided the 3D printing machine. So the idea here is you've just bought a new toy, that really cool 3D printer from GE over on the right, but then you face the problem that it's in this field, it's your responsibility as the purchaser to set up this 3D printing device. Each of these 3D printers is different, it's got different configuration of lasers and lots of other parameters that will affect the quality of the final component that you've printed. And so the typical approach in the field is that you're going to have to perform some trial and error experiments in order to set it up. And so we were brought in to see whether we could instead apply machine learning in order to make the setting up of these machines more efficient. So on the next slide, please, we can see that there's a variety of different approaches that one could take to setting this up. The first, the really brute force approach, is that you write out all of your parameter space in some big multi-dimensional grid, and then you make a grid of experiments that you need to do that might be uniformly spread across that space, and you go bang, 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 do all of those experiments. And of course, you will find the correct parameters if you do this, but the disadvantage is that in high dimensional space, it could require more experiments than the lifetime of the machine or even the lifetime of the universe to get through. And so it's just not going to be a practical methodology. We're going to need to do something a bit more intelligent. So then on the next slide, we can see a different approach, more common in the field, which is you get an expert, somebody that's been doing 3D printing for a decade and has a really intuitive understanding of these machines, to come in, and they will look at the search space and go, well, that bit's not going to work, that bit won't work, this bit's promising, to really drill down and quickly, or more quickly, fine-tune the machine. So that's great, but there are disadvantages to this, that the expert's going to be expensive. The expert may well is going to retire at some point, so then what are you going to do? And moreover, if you're a company like Boeing, then you may well have 3D printing machines in different factories, and you've got one expert setting up one in the UK, you've got a different expert setting up the one in Finland, different experts setting up the one in the USA, and they're going to pursue different approaches. And so you won't have consistent print quality across the world, and so you haven't got a very reliable and robust business. So a different approach that we can see down at the bottom is to go for some kind of structured DOE methodology, where you search through the space. Yesterday we heard a little bit about the Sobol method or Latin hypercubes, which would be able to cover this space more efficiently, but still, is it actually going to be efficient enough? Because it can't take the points that you do and measurements you do are predestined, and it can't take advantage of knowledge that you built up by experiments that you've done in the past. And so this is why on the next slide, we're going to pursue a completely different approach, which is try and use machine learning. So this is going to be great because we're not only going to be able to explore the space efficiently, but we're even going to be able to tell it, what target are we trying to achieve? That we're trying to achieve this kind of print quality and that kind of physical strength of the alloy. It's going to be a flexible approach. We'll be able to scan through perhaps hundreds or even thousands in the extreme case of different input variables that we need to specify. And it's also going to be efficient because it will be able to take advantage of experiments we've done in the past to understand what's going on and then propose the next most important experiment in order to get maximum understanding of our system. So on the next slide, please, we can see the kind of general approach. It's something we've seen a couple of times already during this conference, that we're going to kick off with a few experiments that have been done in the past, some very coarse data here to train up our machine learning tool. Then on the next slide, we're going to be able to then interrogate that machine learning model and ask it, so where next? What's the next most valuable experiment to do? So to understand that a bit better on the next slide, I've got here just a one-dimensional representation of, on the y-axis, one of the variables that we might be trying to optimize, and on the x-axis, one of the input parameters, like how much laser power do we use. I've got here in grey some experimental data points that we have taken in the past and then already fitted a machine learning model to it. So the dark blue is the expected value of the machine learning model. And then I think it was in the discussion session, it was emphasized how important it is for our machine learning models to always show uncertainty. So I've already shown them here with a plus or minus 1 standard deviation lines in light blue. We then got 3 different regions, or 4 different regions even, of the curve. Here in the center, we've got some sort of data that's got very little uncertainty on it. It's arrow straight, and so our machine learning fits it well with small uncertainty. Down in the bottom left, perhaps the experiment was more difficult to do. The experiment itself carries uncertainty, represented here by the vertical scatter of those points, and the machine learning models picked up on that, and so the plus or minus 1 standard deviation error bars on it are larger. Now here in the middle, there's this sort of odd experimental point, which seems to be off the trend, which maybe it's an outlier, the experiment went wrong, or perhaps there's some really cool sort of chemistry that happened here. We made a really cool new material with unexpectedly good properties, and so maybe we need to explore that further. But we can see the machine learning model is partly kinked in that direction and the uncertainty has grown, but it kind of knows it probably is an outlier. And so it's several standard deviations away from where the machine learning model thinks it should be. And out on the right, I've been enthusiastically extrapolating, where the machine learning model's done linear extrapolation, but it knows it doesn't really understand where the curve goes, and so the error bars have grown. We could then ask, where should we do an additional experiment in order to really pin down our understanding of the system? So on the next slide, please, we can see 3 different places which we would hope the machine learning model might consider. Perhaps it would do one out on the right in the extrapolative region, because an experiment there would sort of, maybe it'll be down here somewhere, maybe it'll be up here, but it would really tell us where does the curve go, and that could be valuable. Perhaps we should do an experiment here, where we're in the region where there's the outlier, because perhaps it will allow us to confirm that it is an outlier, or maybe we'll get lots of experimental results right up here and the material's undergone a phase transition, and this is a really important result. Or perhaps we could do some experiments down here where there's the noise, and by taking more values there, they might themselves still have that same kind of experimental scatter, but you'll get a 1/√n improvement in the estimate of the machine learning model. But all of those places where we could do additional experiments are characterized by the uncertainty being large, and that's what the machine learning model would go off and search for. So we could do just that, and on the next slide, we can see that you can go off, get that additional data, put it into your machine learning model, and then you'll be able to train up a better machine learning model in the future. And perhaps one might even then go right back to the top and then ask this better machine learning model, where next should I do some experiments to improve the quality of my predictions? So on the next slide, please, we can see this, how this might work in practice. We've got here, this is a toy model. We were exploring a 5-dimensional parabolic minimum, and I've got plotted here on the y-axis how close the machine learning model is to finding the actual analytical result for the minimum of the parabola. And on the x-axis, the number of data points, the number of experiments we performed in order to train that machine learning model. So both of these axes are logarithmic. And so, of course, what we really want to do is be in the bottom left of this curve. Now, I before rejected the idea of doing the uniform cubic grid of results. That's here called full factorial, the sort of sky blue points that's up at the top of this curve. So that's the worst thing we could do. And then there's an enormous long zoo here of other sort of structured design of experiments techniques, which we see all give a similar trend. They tend to be better than the grid, but it all looks like, in this instance, they've got something like a 1/n type improvement in accuracy on this log plot. However, what we can then do is apply our machine learning methodology to do some experiment, have some experiment results, train the machine learning model, ask next where the uncertainty is large. So on the next slide, we can see what that does. We see it gives a fundamentally better behavior on this curve. It dives much more steeply down. It looks something like 1 over n squared like, and would give a dramatic reduction in the number of experiments, which on the next slide, we can see here that if I was aiming for a certain level of accuracy, so that's a certain horizontal value, y value on this curve, which I've highlighted up there in orange, then we can see that the machine learning approach manages to get there with many fewer, about a factor of 10 fewer experiments than if I were to sample using one of those more structured DOE approaches. And so that's a sort of really powerful confirmation of the importance of using some machine learning, adaptive learning for this kind of system. And so we can now go off and actually apply this to the setting up the 3D printer. So on the next slide, we actually did this in a batch type thing where we said, what's the next most important? So it was of order 50 experiments to do. The G went off, printed those. Here's the samples that were printed. There's a fancy picture of what the alloys look like under a microscope. But on the next slide, we'll be able to see the actual performance of this, where we've got on the y-axis, the machine learning prediction for a quantity, and on the x-axis, what was actually measured in experiment. And we can see, well, firstly, I'm very happy it's all got uncertainties on it. On the whole, it looks like the machine learning predictions matched with the measurements within their expected error bars, apart from this slightly unfortunate point up at the top here, where we can see it's the only one with an enormous experimental uncertainty on it. So goodness knows what happened there, but I think all bets are off for where that one is actually, what actually happened. But for all of the others, it looks like there were good experimental and machine learning predictions. And so we were very excited by this result, and even more pleased that on the next slide, we'll see that Boeing were very excited by this result, and so looking forward to how machine learning could really drive forward the adoption of additive manufacturing within the aerospace business. And so now going on to the final slide, I think. Oh, no, sorry, no, of course. Now, the methodology that I've shown so far, I've shown it for 2 applications to additive manufacturing for alloys, but of course, it's really just a generic approach, a machine learning approach, in our case, very good at handling sparse, difficult, noisy data. And so we've had an awful lot of fun applying it to other problems with other companies. So I'll show here just some others that the company's actually allowed us to write academic peer-reviewed papers about. So up in the top left, we worked with Johnson Matthey to design some catalysts for them that were experimentally verified. We did a lot of work with NASA to first validate or compare this machine learning approach to some others. And then they used the technology to go off and design some heat exchangers for use in space applications. Down in the bottom left, you won't be surprised, we did a lot more work with Rolls-Royce designing some other alloys for other parts of the engine. And in the bottom right, we did some work with ANSYS and one of their subsidiaries, Granta Design, whom some of you might know, sell software called the Cambridge Engineering Selector, which is widely used by engineers in order to select which materials to use. And of course, that is underpinned by a large materials database, of which, of course, would make me salivate. And so we took that, we trained machine learning model on it, and much like the slide where I showed you the outliers, we went through and then did a retrospective looking for outliers in their database, which they could then go away and look up again in primary sources. And so we were really powerful at finding those outliers. We did so with a fidelity of about 50%, and we got here some of the outliers that we found. But the methodology is not even just limited to alloys. So on the next slide, please, we'll see some other cool applications ranging from, on the top left, we do an awful lot of work in pharmaceuticals and drug design. There's some of the companies that we work with. In the top right, it's a cool project with international flavors and fragrances, where we use machine learning to replace a qualitative human measure of how nice does a certain perfume smell. And of course, we managed to, well, we're very fortunate that we were able to predict very accurately that subjective measure, which is great for IFF because they don't need all these expensive humans to come in anymore, and they can instead use machine learning. We also work with BP to design new lubricants for electric vehicles, and in the bottom right, some more work with ANSYS, and in this case, the University of Birmingham on designing materials for batteries. And so we can see that this kind of machine learning is very generic in its approach, and we're very excited about the broad range of applications that we can take advantage of. So then on to the final slide, please. We have shown you today how there are sort of in real life applications in engineering of machine learning often comes up against the buffers because of sparse data. And I've outlined two different approaches that we've taken to get around that. Firstly, to put the human in the loop and get them to use their physical intuition to propose other proxy quantities or computer simulations that we can use to augment our data set. And secondly, the brute force, let's just go out and get more data by using adaptive experimental design. I've shown how we use that to design two different alloys for 3D printing that we went off and experimentally verified, but also underlined how this machine learning is completely generic and the same ideas can be applied across the sciences, in our case, where there is missing data. And so I've had a lot of fun doing this. The technology is originally developed in my group at the University of Cambridge, but now to really drive forward the impact, we're hard at work and taking it to, or have now taken it to market through the Startup Intelligence. So with that, I'd like to thank you for your attention and hope there's a couple of minutes for questions.
Thank you, Gareth, for a lovely talk. Very exciting. I bet there are many questions, starting with Patrick.
Thanks a lot, Gareth. I really liked your design of experiment example. And I was wondering, so what in the end was your objective function? Because you were configuring the machine, right? Did you have some reference samples you were comparing to? Or what was the criterion for being good?
Oh, so excellent. This is a good question. So what we were really looking for was to find prints that were satisfy some target physical properties. So they wanted us to print an alloy that had this number of fewer than this number of defects and this strength, and then separately a different alloy that would be really strong at high temperature, and separately a different alloy with other properties. So in order to do that in that design of experiments, we had to not only go and look where the uncertainty was large, but also we could put like a horizontal line on that graph, and we were looking for materials and processing variables that looked like they could be above that line. They could satisfy the required targets, but we need more information to get there. So that introduces an additional twist that we need to consider. If we've already sort of discovered with very small, very good confidence that we can beat that target, there's no point in doing additional experiments because we've already there. So we were always looking for places where the expected value was above, but the uncertainty was large to get maximum value out of the experiments.
Maybe a follow-up question, if I may. So this objective function that you were working with, you didn't show it, but did you look at it and how close to harmonic or quadratic is it, which would be good for the conventional DOE approaches you were comparing to, and your adaptive design, I think, is probably nonlinear and would do better if the function you're trying to charter is very complex. So can you comment on this?
Yeah, so the function is definitely sort of rather complex. These alloy spaces, they tend to undergo a lot of phase transitions. And I showed you in my, so the first example, we made a 2-phase alloy, so it was a gamma-gamma prime alloy, but there was another 58 phases that could form in this alloy that we wanted to avoid, and there were 2 in particular that you really want to avoid. And if you look at phase diagram charts, you find there's like up, down, everywhere, and you have to navigate very carefully through that space in some very narrow ranges in order to design an alloy. And so we really need sort of a methodology that's very numerical, very non-linear, that it will be able to find the appropriate solutions.
Hello, Gareth. Thank you for a very lively talk. A question about, I guess, about commercialization. So do I need to be worried that my flight home is going to be on a machine learned jet engine, or how much can this accelerate sort of commercialization? And then a very quick follow-up as well is about, you didn't mention using any theory here at all. Is that just, irrelevant to these kind of problems, or, do you see theory still having a place in validating some of your model predictions?
So I am now very careful about which flights I book to hedge my bets. I don't want to fly on a plane that I was slightly involved in designing, but I don't think you need to be too worried that the tooling that we've proposed or are now working on is only used in the very initial stages of alloy design, that it proposes alloys and then we make them in the lab and then they get handed on. And then the companies just have a list of alloys that typically come from different universities, which they then spend years and years and years testing and slightly fine tuning in order to get them so they could be manufactured at scale. And so I think we could be confident that the alloys will have been properly tested. Now, about first principles methods, they are important for us. In the first project, we were using a method called CalFAD very heavily. So that's one that predicts the thermodynamics of alloys, which phases are going to form in them. And we would first perform in our database, it was aboard 150,000 CalFAD calculations in order that our tool could have a really good understanding of all of these pesky phase transitions. And that was regarded as one of our input properties, just like weldability, which we could then correlate to the strength properties of the alloy. And so we were guided by those first principles calculations. And we also sometimes use density functional theory calculations, like in the to design batteries and in the BP projects. We were heavily reliant on molecular dynamics calculations to understand some properties of lubricants.
Any further questions? Oh, okay. First Kunal and then
I have two quick questions. So one was in the plot where you showed the measured value versus the predicted value, there were a lot more points on the top right versus the rest of the points.
So that was here.
Yeah.
Yep. Yeah, so I think in that instance, that's because they were actually interested in what was going on in the top right. And so, as I said, it was target driven, and in this instance, they wanted to maximize the target.
Okay. And then the second one was with the perfume example, because then that's subjective, right? So how do you have like somebody say which one was more fruity versus more something else? So what was the objective?
Yeah, so there were several of them, several different measures, but it's just that somebody, that they'd had panels of the general public come in the past and measure, record how nice this thing is and mark out in a 5-star rating, or how fruity it was in a 5-star rating. And the problem with those panels is each human's a bit subjective, and so they tend to have quite large panels in order to get an average of results, which is expensive. And so we were brought in, and now they have adopted machine learning to provide the initial guidance of where they should search, because we can do so with slightly better reliability than the human. And then it's just before they're going to take the thing to market, they would revert back to their sort of, well, older business model, and then get the panel in just to get the final score.
okay, go Matthias and then Jari. Question from Zoom.
Thank you for the very nice talk. I'm also interested in the adaptive design of experiments. If we could go back to the example where we had this tenfold increase or decrease in number of points we needed. Yeah. So this is really on experimental data. This is also for the alloys.
This is on an analytical 5-dimensional parabola.
Okay, I see. I see. So this is a quadratic function.
Yeah.
And still, the adaptive design of experiments does so much better than the. Okay.
But of course, it's well, on a log scale, it didn't do that much better initially. So what's the laser pointer? So that's 10 points. That's if you got 100 points. And it's even around about here, it's still vaguely similar. So it's only when you're trying, in this instance, getting right down into the minimum of the parabola and trying to find it to the 1 in a millionth accuracy.
So there's no third order terms, but there's noise or
not in this example.
But wouldn't you get a perfect fit then already with a few points when it's a purely quadratic model?
Yeah, it depends what your machine learning model is. Of course, if ours was fitting a Taylor expansion or some form of Parday approximant, then, well, absolutely, we would only need sort of 10 or so points and would fit it perfectly. But the machine learning model we were using here wasn't. And so there's no fundamental reason why it should fit well.
But with design of experiments like non-machine learning, shouldn't they fit it with a lot less points?
Well, only if they were fitting a parabola as well and or the point happened to perfectly by luck line up with the minimum of the parabola. Like if it had been set up to be completely central in the box, then the full factorial method would have hit it almost on the first point. And so it's a little bit of a toy playing type thing, but we also need some form of toy model to be confident that it was working and the fundamentals are working before we go and worry about noise and multiple minima and goodness knows what other problems.
Right. Maybe if I can ask a quick other question. So how important is the initial exploration for the adaptive design, or is this somehow fine-tuned in this example, or also the acquisition function?
Good question. We don't quite know the answer to this. So what we are currently doing is having quite a simple, it was just one of these methods down the bottom, one of the Latin hypercube methods to recommend the initial endpoints in order to do. But yeah, we haven't done a really careful study of a better thing than that. And if you know something better, I'm all ears.
Oh, I wish I knew. Thank you.
Thanks.
Okay, and this is from Pierre-Paul de Burke. So first of all, where do you get your training data? From literature or open databases? And secondly, how do you deal with missing manufacturer parameters?
Oh, both good questions. Right, so the training data, some of it comes from the literature, some of it comes from those first principles calculations like the CalFAD, but a lot of it comes from the company that we are working with. This is in many ways not that academic work, and we're the very practical end. And each company has some really strange idiosyncrasies in their factory. Like they have worries with some of the parameters we do with which windows do we have open in the factory and what power do we set the ventilation fans to, which are very important for making these materials on bulk, but are completely not reproducible on going across different factories. So yes, the bulk of the data will come from the company that we are dealing with. And yeah, missing manufacturing parameters, these are huge trouble for us, especially in the early days when we were working with Rolls-Royce, and some of the data came from dusty filing cabinets where it just said, we annealed it, but they don't record the times and the temperatures. And so then that is what was part of the inspiration behind doing the missing data, that one might hope that the effect of annealing sort of hits upon the several of the strength properties, and you can use one strength property that you've got more data for to imply what the manufacturing process was, and then in the second machine learning model you'll stack on top of that to go from that to go and repredict one of the other physical properties of the material. And so that's exactly the kind of problem that we were sort of set up to focus on.
Okay, I think we've had a really lively discussion session, and Gareth is still around, so you can ask him during the coffee session too. So thank you again. And now it's lunchtime, and the program starts again at 2 o'clock.